This video is about a modification of Gauss-Jordan elimination called Gauss-Jordan elimination. Now, let's remember what the goal of Gauss-Jordan elimination is. The goal is to take an augmented matrix and perform some row operations that will put that augmented matrix into row echelon form. What's row echelon form? Again, it's a matrix that satisfies the first three properties listed here. First one is that rows of zeros are grouped at the bottom. Second property, the first non-zero number in a row with some non-zero entries is a 1, so that's called a leading 1. And the third one, which I like to write as leading ones appear diagonally. So diagonal doesn't mean a perfect diagonal, but as you move from left to right, the next leading one is a bit further more to the right than the previous one as you go down the rows. So that's row echelon form. Row echelon form is this. Now, if we add a fourth property, which is that each column that contains a leading one has zeros everywhere else in that column, that's called, well, that matrix would now be in reduced row echelon form. Let's write that. Reduced row echelon form. So that's if we add that fourth property. Now, the algorithm that will bring us into row echelon form is Gaussian elimination. Gaussian from the famous mathematician Gauss. Elimination. There's an E. Elimination. And the algorithm that will produce a matrix in reduced row echelon form, that's Gauss-Jordan. Gauss-Jordan elimination, which is the topic of this video. Okay, so I'll show you how that's performed. Now, the idea of Gauss-Jordan elimination is that you first do Gauss elimination and then you perform an extra step. So it's essentially an extended version of Gauss elimination. Gauss-Jordan comes from Gauss, Carl Friedrich Gauss. He's a German mathematician, maybe the greatest mathematician of all time. Lived in the 18th, 19th century. He's known as one of the greatest, if not the greatest mathematician of all time, because he did work in many areas of mathematics that laid the foundation for modern mathematics in those areas. Wilhelm Jordan, on the other hand, I personally don't know much about. He's actually not a mathematician, so he actually helped to promote the method, but he was working in geodesy, which is a discipline that is about how the earth is shaped, and so it has nothing to do with, well, it has a lot to do with mathematics, but he didn't per se do mathematics on his own. And he's not a Jordan that, if you hear about a Jordan in mathematics later on, there's another one, but that's there's a French mathematician called Camille Jordan, and he did actually work in linear algebra, but I initially thought those were the same Jordan, but they're not. One is, actually Wilhelm is also German, so one's German and one's French. So what I've decided to do is go back and revisit the example of page 14 that we had done. And there was a linear system that we had initially solved using Gaussian elimination. So we had written down the linear system in its augmented matrix form. Then we had done Gaussian elimination. We did that. Once we had done Gaussian elimination, we had obtained here a matrix in row echelon form. Okay. So we have we don't have rows of zeros anywhere, but so first property is satisfied, right? The rows of zeros are stacked at the bottom, but there aren't any here. Any non-zero rows, which is any row here, its first non-zero entry is the leading one, so I've highlighted those in orange, and they appear sort of diagonally. So that's the third condition. Leading ones are associated to leading variables. So my leading variables are x1, x3, and x5. Those are all also highlighted in orange. And after that, to recover the solution, we do a backward substitution, which means that we assign parameters to the free variables, which are x2 and x4, so s and t. And then we start with the last equation, and we solve for each of the leading variables. So x5 is going to be 2. X3 is going to be minus 6 plus 7/2 x5. So replacing x5 by 2, we get that x3 is 1. So we did all that work before. So this is why I'm going a bit fast here. And if we solve the first equation for x1, we get this. Replacing x2, x3, x4, x5 by their the values we already obtained, we get this, and then it can be simplified to 7 minus 2s minus 3t, and finally regrouping everything together, we get our final solution set, right? And it's a solution set because, well, what I mean here is there are more than one points because s and t could be any real number. So by assigning values to s and t, you can recover all the points that are solutions to this linear system. Now, the difference with Gauss elimination is that at this step, you do an extra step. So this is Gauss-Jordan that we're going to do. So I'm going to assume we have done Gauss elimination now. And to do Gauss-Jordan, it's you can look in your book. It's on page 15. So I'm just going to go and essentially show the what you find on that page. We do step 6. Step 6. I'll read it to you. It's a bit complicated, but you'll see it's actually quite simple to apply. Beginning with the last non-zero row. So in our case, this is the last non-zero row, right? Because I don't have rows of zeros stacked at the bottom. So in our case, beginning with the third row and working upward, add suitable multiples of each row to the rows above to introduce zeros above the leading one. So I need to add multiples of row 3 to rows 1 and 2 in order to introduce zeros above that leading one that I have in row 3. So essentially, for the Gauss-Jordan step is above your leading ones, you will introduce zeros, and you start with the rightmost leading one. So we start with the rightmost leading one, which is in row 3, and we want to introduce zeros above it. So right there. Okay, so how do I do this? We're gonna add or subtract multiples of row 3 to rows 2 and 1. So row 2, to make the minus 7/2 a 0, I will add 7/2 of row 3. And for row 1, and I can do 2 operations at the same time because they both only involve row 3, which is not changing here. We will subtract 6 times row 3. So row 3 is not changing, but the other two are. And if you do this, you're going to get 0, 0, 1, 0, 0, 1. And subtracting 6, we get 1, 2, minus 5, 3, 0, 2. And in your book, they do this in 2 steps, but you don't need to. You can do it in 1 step because only row 3 is involved here, and it's not changing. And after that, okay, so we've got our zeros here, so that's good. So now I want to introduce a 0. Where's the next leading one? It's right there. So I want a 0 above it. So right there. So to put a 0 there, I will subtract a multiple of row 2 now, because that's the one that includes my leading 1, in the third column. So row 1, you will add 5 times row 2. And if you do this, you're going to add 1, 2, 0, 3, 0, 7. And the other 2 rows are not changing. Like that. And then this matrix now is in reduced row echelon form. So it's in row echelon form, but on top of this, for every row that has a leading 1, the other entries in that column, so did I say it's for every column that has a leading 1, for every entry in that other entry in that column, that entry is a 0. Okay, so that's when you know it's in row echelon form. Okay, and then what we can do here is, it's still a backward substitution, but you'll see it's a lot easier when we want to recover the solution set. Backward substitution. Let's spell this right. Substitution. But you'll see it's a lot easier. So once again, we identify what our variables are. We know that those are the leading variables. Okay, so I will assign parameters to the free variables and do my backward substitution. So I start with the last equation. It says x5 is 2. That's the last one, right? This one. And after that, the second equation is x3 is 1. So you see, I don't have to do any work for x3. So compare this to here. So here I had to do this work here to get x3. I don't have that work to do. That's because it was kind of done when I'm doing the Gauss-Jordan step, that other step, that extra step. And I solve for x1. You'll see I have no work to do for x1 either. x1 is 7 minus 2x2 minus 3x4. So technically I could even write immediately 7 minus 2s minus 3t and not do any work again. So this compared to this, there's no work to do here to recover the 7 minus 2s minus 3t. So essentially the work that's done here is moved here. So we haven't gained much in the sense of we don't have a method that's faster to work with. So Gauss-Jordan is not faster to work with, even on paper, than Gauss-Jordan, than Gauss elimination. It's just a bit different. It's just you trade the work you do in the backward substitution for the extra step in Gauss-Jordan. But then afterward, the reward is that backward substitution is a lot easier. So then when you regroup everything together, you see you've got the exact same solution set as before. So x1 is still 7 minus 2s minus 3t. x2 is s, x3 is 1, x4 is t, and x5 is 2. Okay, and that's exactly the same as what we had before. Same answer. So that's it. That's what Gauss-Jordan is. But I guess the big highlight is that it's an algorithm to write your matrix in reduced row echelon form.